Okay, good. I have no idea who is here.
Well, you can see some of the figures, I think.
Oh yeah, I see our speaker. Wonderful. Hi.
Right. Hi.
Hi, I'm Stefan. Great. My camera is a little bluish. I have the feeling. I don't know what's going wrong with this thing. Okay, let's see.
Oh, well, small detail.
Okay, Ramin, you are doing the host thing, right?
Yes, I will introduce the speaker. I don't plan to speak that long. Just
okay.
Introducing him.
Yeah, before I mute myself, I just wanted to say I really appreciate we have you as a speaker and also in our SAB. Wonderful, wonderful. Welcome, welcome, really,
You're
to the
welcome.
Institute.
Okay, so it's 5 o'clock. Shall I start?
Sure.
Oh, yeah. Okay, so good afternoon, everyone. Welcome to this special colloquium, this Prandtl lecture. So we, every now and then, our institute, MPIDS, runs public lectures in which we invite a distinguished guest to address the public in general. Well, it used to be people in Göttingen, and we used to run it in a big church in the city center, where we can basically ask them to let us host an event for the public. Now we are in Zoom era, so we are doing it in Zoom or on Zoom, and we're also live streaming it on YouTube. And we have invited several guests from Göttingen, but also friends of the Institute and colleagues from nearby institutes and the physics department of the university, Max Planck Institute for Biophysical Chemistry, our neighbor, and the university hospital, medical center, and lots of other places. So welcome to all of you. It's a great pleasure for me to introduce our speaker, Professor Michael Kostelitz. He is a very distinguished theoretical physicist and well known to most of you. I don't plan to say much about him because I think from the title that he gave, I expect that we're going to hear quite a lot about the trajectory and the different steps that he considers important in his career later on. I'll just say that you know, personally, as a physics student, when I read his work, it was many years ago, probably 25 years ago. It was a significant moment in my career because I found it as a very good example of how theoretical physics can bring about different areas, can bring unique perspectives by combining different fields. For example, in the case of his work, bringing in topology as a fundamentally new tool, if you want, to study the physics of phase transition, something that maybe before that people would have considered completely irrelevant, but what he did created a new way of thinking and a new way of basically studying the phenomena around us, collective behavior of various solid state systems like superfluids and two-dimensional magnetic systems, as well as melting of solids in 2 dimensions, and so on. He has been a high-energy physicist before turning into solid state and statistical physics. So we will hear about these, how he picked up different key contributions or ingredients for the development of his career. And I also had the pleasure in my Oxford years because he was from the Oxford School, as it were, from the Rudolf Pals school, to hear stories about him and his achievements. And we are very also honored that he accepted to be on our advisory board at MPIDS, because what we also want to achieve in our institute is basically being able to make contributions of similar spirit, to bring in different fields together and to tackle problems with new tools, and try to understand very complex things using the tools of mathematics and theoretical physics and experiments. So with this very quick introduction, I would like to hand over the floor to you, Professor Kosterlitz. We look forward to your talk very much, and thank you for being with us.
Well, thank you very much for that very flattering introduction, because notice the first slide basically has a title and then the subtitle, which is what I'm going to talk about. The subtitle is A Random Walk Through Physics. And it was a random walk, because when I was younger and a postdoc and so on, I had no idea really where my career would lead, and so I just, how to say it, went with the flow. So let me start now. I was sort of born in Aberdeen. Well, okay, first of all, I have a couple of, okay, here we go. So just to prove that we actually were in Stockholm, at one point getting the Nobel Prize, here's my favorite photograph of proof, because there's me in the middle. There's at the Nobel ceremonies in 2016 in Sweden. There's the king standing to the right of my wife, and the queen standing to the left, to my left, and the rest of the royal family is scattered around. Just one entertaining episode was that at the formal banquet for the Nobel Prize, I had to escort the Crown Princess Victoria of Sweden to dinner, and I was feeling a little bit wobbly, and we had to walk down these long stone stairs, and my balance wasn't too good. So I was wearing these slippery, fancy evening shoes, and I was terrified of slipping and falling and dragging the Crown Princess down with me, which was so that was quite an interesting experience. However, things went off all right, and then, of course, this banquet was scheduled for about several hours, not just a quick meal by any stretch of the imagination. So I was wondering, how on earth was I going to survive the banquet, because it was an awful lot of alcohol provided. Basically, it was a different drink for every single course, and there was a lot of courses. And so I thought, since I was sitting beside the Crown Princess, I thought, well, okay, obviously she's been to several of these types of events, and obviously she knows what she's doing. So I will follow her lead with the drinking. And so, to some surprise, when the first course came and the first drink came, she basically drank the lot. And so I thought, all right, if that's the way it is, I'll follow suit and see what happens. But what was interesting was that was the only alcohol she drank during the whole banquet. So I thought, oh, that's a smart idea. I'll do the same thing. So I survived a 5-hour eating and drinking orgy without embarrassing myself too much. Anyway, I was really surprised. I was really surprised that I to get the Nobel Prize, because the way I heard about it was I happened to be on sabbatical in Sweden, in Finland, and a colleague and I were in an underground car park in a city called Espoo, which is just outside Helsinki, waiting, about to go up to the mall for a sushi lunch and beer. And my cell phone went off my pocket. And I eventually managed to extract the cell phone and answered it. And a strong Swedish accent came over the phone and saying, blah, blah, Nobel Prize. At which point I sort of was so surprised, because this was 2016, and the work we'd actually, which I thought had been pretty good, we'd done in the early 1970s. So it was a number of years. And I thought that basically everybody had forgotten about it. And so I was so surprised that I tried to think of something to say, like thank you or something equally banal, but I couldn't say anything. And I was so astounded that I was basically, my mouth was opening and closing, and nothing was coming out. And eventually, after about 30 seconds complete silence, the only thing I could think of saying was Jesus, because I was so surprised. But anyway, now, so my fellow laureates, physics laureates in 2016 were David Thouless, with whom I developed, or he and I had developed the theory of the phase transitions in 2 dimensions, at least in the XY model, and superfluid helium films. And then there's Duncan Haldane, who was also got the Nobel Prize that year, shared the Nobel Prize. And when I first heard about the division of the money, I thought, because what happened was that David Thouless got half the prize, and Haldane and I got a quarter each. So I thought, hey, that's not completely fair. It should be a third each. But then I realized, after thinking about it a bit more, I realized that the Nobel Committee had been smarter than me, because actually the prize was awarded for 2 separate but related pieces of work. And these pieces of work were each done by 2 people. And so the prize was actually split 4 ways. But this, unfortunately, has contradicted the rules of the Nobel Prize, which say that it's a maximum of 3 people for any particular subject. So fortunately, the conditions obeyed the constraints of the Nobel Prize, because 2 of the people involved in this were the same person, David Thouless. And so that's why he got half the prize, because he was involved in both pieces of work, while Haldane and myself were involved in only 1 piece of work. So now, let me tell you a little bit about how I got to to Stockholm. So basically, I was born in Aberdeen in Scotland way back when in 1943. And there's a photograph of my father, who's the big person, and this small kid is me at about age, I don't know, three or something, 3 or 4, something like that. Sort of looking at it, we're outside our granite house in northeast Scotland. And looking at this young person, he sort of, to me, he looks like somebody who was, you know, anxious to get away and get into yet more mischief. And so I you know, had quite an interesting upbringing, because my father is a refugee from Hitler, and he came to to Scotland. I think it was 1934, 32, 34, because, you know, was working in the Charité in Berlin, and at one point, Hitler decided that anybody who had some Jewish connections or origin, yeah, they could continue to work, but not to be paid. So my father realized that things were simply not good. He used his contacts in Britain and looked for a job in Britain, and was offered a few. But Aberdeen University, you know, Aberdeen was a rather minor university in the northeast of Scotland, but they offered him a permanent job, which he accepted. And of course, there was 2 reasons why Aberdeen was very, very attractive to my father. It was first the security of a permanent post, and the second thing was that there was a Nobel Prize winner called MacLeod was there, and my father wanted to work with him. But unfortunately, MacLeod had the bad grace to drop dead shortly after my father's arrival, so he had to make his own presence felt. And he worked in Aberdeen for about 60 years, finally quitting at age 90, when old age took over. As one slightly, I guess, one unfortunate aspect to my father's career, in that it was called really the father of the opioids. So I guess that one could argue that my father is responsible for the present opioid crisis, of addiction crisis, but must say that my father recognized very early on that, you know, because he described the opioids as a naturally occurring substance in the brain. It's an interesting story about that, because in order to get enough material to experiment on, he and a young colleague went to the Aberdeen slaughterhouse and negotiated with the slaughtermen with a good bottle of scotch for pig's brains. And so they got a load of pig's brains and then transported these back to Marshall College, the university, and then pounded these brains into a paste in the men's john downstairs, which had a nice tile floor, and then experimented on it and found this, what he was looking for, this naturally occurring enkephalin, which is a small molecule, basically part of the endorphin family. And then he wanted to use this as a painkiller. So he tinkered around with it chemically, but unfortunately, to make it more stable. But unfortunately, when he produced a more stable version, it was incredibly addictive. So he basically gave up on that. But of course, other people, you know, now the basic opioids called, what's it called, fentanyl or something, and it's used as a drug. You know, it's one of the addictive versions of the stuff my father had been working on. Now, so basically, I went to school in Aberdeen, a semi-private boys' school, Roberts College, where I received a very good education. And the nice thing was that I could give up the subject I disliked when I was about 16 and concentrate on the ones that I did like. And my parents never overtly tried to influence my choice of study, but I naturally gravitated towards mathematics and the sciences. I disliked intensely all the humanities, literature, languages, fine arts, etc., etc. I think this was because of my very poor memory. I like to say that I can remember a maximum of 10 facts, but I'm not too sure about the last 4. And so anything that I do has to be basically deducible from the 6 facts that I'm sure about. And certainly all the humanities subjects are very memory intensive, and I always struggled with those. But the mathematics and sciences I could handle with a minimum number of memory, and use logical deduction, and this really suited my way of functioning. Now, my education was, you know, a bit torturous, because when I was about 16, my father decided that I might be good enough for Cambridge University. So I was sent to a school in Edinburgh where the teaching went up to the English A and S levels as needed for the best English universities. And I got through this fairly easily, again, getting, you know, top grades and so on, and was accepted at Cambridge with a prestigious scholarship to study the natural sciences, which, to my great pleasure, did not include any other subjects. Now, initially, I got a bit bored with teaching because I'd learned almost all of it at my Edinburgh school. However, the chemistry was fun, but I got turned off it by an incident where I had a test tube of a colorless fluid, and I was just simply staring at it, wondering what on earth I was supposed to do with it, when suddenly it started to change color. And I thought, oops, this doesn't look very good. So I held it out to the side at arm's length, and then it had just exploded and sent shards of glass into my cheek. To this day, I've got no idea what happened. But there were 1 or 2 other incidents where I discovered that in fact, I'm red-green blind, which makes distinguishing test tubes of different shades of reddish liquids rather difficult and sometimes dangerous. As an aside, I'm sure you can imagine the sort of problems that being red-green blind cause when you're driving a car and there are traffic lights in the distance, because I can't really distinguish between a red light and a green light. Basically, I have to go by the position of the light. Now, these difficulties, together with my poor memory, made me decide to go for the simpler but safer subject of physics as my concentration. But my academic Cambridge career also got disrupted when I joined the Cambridge University Climbing Club and discovered the joys of rock climbing. Because I was actually, although I say it myself, I was actually quite good at it. I enjoyed it very much, and quickly became addicted to it. And here's a picture of me. I'm at the back, and there's a couple of my climbing partners. In the middle is Mick Burke, who unfortunately died in Everest some years ago, and in the foreground is a British climber called Martin Boyson, who was actually very good. Let me say that there's nothing to compare with the rush I get, when you step out into the unknown, high up on a steep cliff, knowing that a mistake could have serious consequences up to and including death. And this concentrates the mind to an amazing degree. And so the climbing became, and it's also this is a very addictive thing, because this climbing actually became my main interest at university, followed by physics and my newly acquired Swedish girlfriend. And so, not surprisingly, I didn't do as well as expected in the final exam. So I completed a 4th year at Cambridge doing part 3 mathematics or applied maths to try to rescue my academic career. But my climbing passion intervened again, and I didn't perform as well as I'd hoped. I was turned down for graduate school in high energy physics, which is what I wanted to do because it's the glamour subject, and it was the most exciting aspect of physics around. And I was turned down for graduate school in high energy physics, high energy theory at the Department of Mathematical and Theoretical Physics at Cambridge. Ironically, I was actually offered a place as a graduate student in physics, experimental physics, with Sir Neville Mott to study solid state physics. But I turned down this offer in favor of going to grad school at Oxford in high energy physics theory. And of course, it was very ironic that I turned down the opportunity to do graduate study in solid state physics, because that's the field at which I ultimately got my Nobel Prize in 2016. Okay, in Oxford, I worked on what are called dual resonance models, otherwise known as the Veneziano model, which I believe is a precursor to modern string theory, which you may have heard of, and published a couple of papers which have probably never been read by anybody except the referees and my advisor. On completion of my DPhil, as it's called in Oxford, in 1969, I was awarded a 2-year Royal Society Fellowship, which I could use anywhere in Europe, as was my closest friend at Oxford. So my colleague, my girlfriend, my Swedish girlfriend, Berit, who is now my wife, and I went to Torino University in Italy for the postdoc. Now I chose Torino because of its proximity to the mountains, but the physics was also pretty good there in the persons of what they called Sergio Fabini and Tullio Reggi. The three of us, Dennis, my Berit, and I, rented and shared an apartment, and of course then we went to the local shops in Torino to buy food and so on. And this arrangement made the ladies in the local milk shop very curious, because they could never figure out which of the two males this female belonged to. And of course, neither, but this was 1969 after all, some time ago. Basically, I had a wonderful year in Torino. My scholarship in the Royal Society was sufficiently generous that Berit and I could eat well and go skiing in Italy, France, and Switzerland every weekend, and for the occasional week in the winter. Of course, it helped that I had climbing friends renting apartments in Verbier and Lausanne in Switzerland, we could always sleep on the floor for a night or two, so we rarely had to pay for hotel rooms. I also managed to continue with my rock climbing and did some climbs in Italy which were not repeated for several years. Yeah. One time we were driving up, the Italian climbing partners and myself were driving up a narrow road in the Val d'Orco in northern Italy, looking for somewhere to climb. And basically, I thought when I saw this valley, I thought I had entered paradise, because on both sides of the valley there were square kilometers of unclimbed rock. But you must remember that I came from Britain, where cliff climbing was a highly developed activity, and almost every square foot of rock had been climbed on. And to find such an expanse of virgin unclimbed rock was basically unheard of. And so I was aching to set up as many routes as possible with my Italian climbing friends. Now, as we drove up the valley, we passed a boulder about 6 meters high or so, 6 or 7 meters high, with a thin crack splitting one of its slightly overhanging sides. In fact, this slide shows the boulder. There it is on the right, and the crack is going up. It's the quality of the photograph isn't too good. The crack is running up, sort of coming up to the left-hand side of the face. You can just make it out. And this arrangement on the left here is the start of the tunnel, which the road now goes down. And when I saw this crack splitting the boulder, I yelled in Italian, my rather basic crude Italian, "Stop the car!" And I jumped out, put on my climbing shoes, and mashed up the crack, which is now known as the Fessura Costolets, and apparently it's quite famous in the climbing world. I mean, I found it quite difficult. Not the hardest thing I'd ever done, but quite hard. And my climbing partners couldn't repeat it. And as a matter of fact, as I understand it, it took almost 10 years before that crack was climbed again. And of course, by now this has been climbed hundreds of times, and this boulder has actually been preserved by the Italian mountaineers because of this problem, the Fessura Costolets, which, so apparently it was that boulder was due to be demolished, but the Italian climbing world decided, no, that's not good enough, and they managed to get the road diverted around the boulder and preserved it, and managed to preserve it. And apparently, as I learned when I visited, Torino again in 2018, that this rock is now an important feature of the village of Cerasoli. In February 2018, we were actually invited back to Italy, and I got an honorary degree from Torino, but also the local climbers decided that I should be, they should make a fuss, about my exploits, my climb exploits in Italy. And to my surprise, I was told that this rock this boulder, that actually the tourism in the village of Cerasoli, which is about a mile further up the valley than the rock, has been booming ever since, because climbers apparently come from all over the world to try their luck at the crack. And this is a very important part of the economy of the village of Cerasoli. Now, back to my footpath, my physics path. The obvious place to go after Torino was CERN in Geneva because of the physics, and of course for me, the mountains. Let me just there's somebody trying their luck on the crack. You can see that's the crack in the boulder. Yeah. It's quite hard. Apparently, a couple of people, one or two people, have fallen off it and hurt themselves quite badly. Now, the reason I wanted to go to CERN was because I was still working in high energy physics. And both my colleague, shared the apartment in Torino, and I sent in applications to CERN. He was accepted, but in my usual disorganized fashion, my application was late, and I got the reply, sorry, all the desk space is gone, please apply again next year. I now faced the prospect of unemployment. But my girlfriend, Berit, just stared at me and muttered some very uncomplimentary epithets, walked down to the Torino railway station where she could buy an English newspaper with academic job advertisements in it, and came back. Sat me down at the kitchen table, opened the newspaper, pointed and said, apply. So under the circumstances, I didn't have much choice, so I applied for a couple of positions in Britain, postdoc positions in Britain. I was offered all the places I applied to, but I accepted a 3-year postdoc position in the Department of Mathematical Physics at Birmingham University, and rather reluctantly signed the contract. Shortly afterwards, I got a letter from CERN saying that they had decided that they'd have 2 people per office instead of just 1, so I could go there because there was now space. I immediately said to my girlfriend that I would renege on my contract with Birmingham University and go to CERN to have fun in the mountains, which is what I wanted to do from the beginning. However, both my girlfriend and my father were of the opinion that having signed the contract, I was sort of committed to go to Birmingham. And I fought and lost the battle with them. And so I went to Birmingham, because now Birmingham at the time was a large industrial city in the flat middle of England with no mountains in sight. And it was the last place I wanted to be. However, Birmingham turned out to be quite a nice city to live in. And despite the terrible unemployment of the early 1970s, because of the car factory closing, the university was good. The Cadbury estate was a nice place to live, to bring up a family, and we made many friends. So my first real job was in the Department of Mathematical Physics at Birmingham University, first as a research fellow, then as a lecturer, senior lecturer, and finally as a reader. in hindsight, it turns out, of course, that professionally, Birmingham University was the best place I could have gone to. Although at first it was very hard to believe that that was the case. Now, in the first year or so, I continued with my long high energy calculations, and I was on track with writing up my results for publication a couple of times, but both times I was thwarted by a group at Berkeley who published first. I just could not. This was a group of about half a dozen people who were trying to do exactly what I was doing, and I just couldn't compete. Now, as I mentioned earlier, I was fairly good at rock climbing, and I was really addicted to the sport. So I started to seriously consider giving up physics to become a professional climber. And I probably might have succeeded at this, at least, but I certainly was good enough technically at the climbing, but fortunately, Berit, my girlfriend, who's now my wife, of course, vetoed this idea of becoming a professional climbing bum. Now, as an aside, a few years later, after I lost the battle with my wife, and I came down with a neurological condition called multiple sclerosis, which really messed up my balance and destroyed any climbing ambitions I had. And I had to make do with my day job as a physicist and teacher, which simply does not need the same athletic ability. Now, back to my story. I was very upset with the Berkeley group and descended on my colleagues asking if they might have an interesting problem that I might try to solve. As luck had it, David Thowles had an interesting problem in condensed matter physics. He was interested in a class of unsolved problems of phase transitions in 2 dimensions. And, such as the onset of superfluidity and superconductivity in very thin films. I found his ideas, and I think the word topology also appeared somewhere in our discussions. I found his ideas very difficult and challenging, but they started to make sense. And in fact, Birmingham was the place where I learned what physics is really about. And it was a fascinating business working with one of the truly great minds of physics. David Thowles is basically a genius. And almost everybody else, his brain works at a level above almost everybody else. And so he was quite difficult to talk to as an ignorant postdoc, because he had this bad habit of, when you're trying to explain something, of just looking at you and saying, it's not quite like that, it's more like this, and explain to you in a few minutes exactly what you'd been struggling with for weeks or days. And so he'd never nasty, but you see, he was clearly so operating on a level which so much beyond me that I had quite a lot of difficulty in in bringing myself to ask him questions. However, there was one time when he was explaining to me something, and I was in his office listening to him as he was writing on the board. And then after about 20 minutes, half an hour, I realized that I was completely lost and couldn't understand a word of what he was talking about. And, I hadn't understood anything from the very beginning. And so eventually in desperation, I said, David, I'm sorry, I have to stop you there. Could you please tell me where the first equation you wrote on the board, where did that come from? And he turned around, looked at me and said, didn't I tell you that? And I could honestly say, no, you didn't. At which point he said, oh, and then proceeded to give a very clear explanation of what he was talking about. And that incident actually gave me the courage to basically ask him stupid questions and argue with him, because I always just said, okay, if I assume that he'd done the same thing and forgotten to explain something important at the beginning of the discussion, then it's obviously his fault that I wasn't understanding anything. And this attitude, although completely wrong, of course, gave me the courage to ask him, keep on asking the stupid questions. And fortunately, and he actually seemed to appreciate this, and we got on very well together. And together, between us, we managed to solve one of the remaining puzzles about phase transitions in two dimensions, or thin films, if you wish, for which I eventually got my quarter Nobel Prize. And that is when I really realized that physics is something I could devote my life to. And physics was something which I could do even with my slight physical disability due to this neurological disease of multiple sclerosis. Now, despite what one reads in accounts of Nobel Prize winners' progress, I think that my story is anything but that, because I like to think of my journey to Stockholm as a random walk through physics, because the Nobel Prize is a combination of, I think, 95% dumb luck and about 5% smarts. And the luck was being in the right place at the right time with the right people and doing the right problem. Well, the smarts is the ability to do the necessary arithmetic. And although it certainly did not seem so at the time, the right place was the Department of Mathematical Physics at Birmingham University. And the right time was the early 1970s, and the right problem was the problem that David and I solved. And of course, the right people, the right person was David Thowless. And I hope that this story about my crooked and at times seemingly aimless path from Cambridge to Oxford to Torino to Birmingham that led up to my Nobel Prize winning work gives some of you hope, because, it's particularly the students in the audience, there's often a light at the end of the tunnel, no matter how difficult the path that you're on seems to be at the time. Okay, now, let me spend the last few minutes telling you a little bit about the physics. Okay, now this is some data taken from a PhysRev letter in the early 70s of some data about a helium film adsorbed on a resonant crystal, on the surface of the resonant crystal. Now, it's a very thin film, 2, 3, 4 atomic layers thick. And so you would expect that the helium atoms will simply stick to the surface of the crystal. And so when the crystal is vibrating, the atoms, the helium atoms, will simply stick to the crystal surface and vibrate with the crystal. But of course, and these helium atoms will just increase the mass of the resonant body and therefore reduce the resonant frequency. And so on the vertical axis is a reduction in the resonant frequency from its value without any helium film absorbed on it. And the horizontal axis is basically a measure of the coverage of helium on the surface. And so the solid line is the theoretical expectation if, just the resonant frequency just caused by an increase in the mass of the resonating crystal. And the experimental data is shown by these little circles, and we see that the experimental points you get to the line, as the coverage of helium increases, the expected straight line, and then follow the straight line for a bit, meaning that all the helium is stuck to the crystal and is moving with the crystal. But then when the film gets enough helium is absorbed, notice that the experimental points break away from the expected classical frequency, and there's a big discrepancy for larger coverages of helium. And this was the problem that David Thouless really wanted to understand, because the data indicates that this thin layer of helium on this vibrating crystal has decoupled from the crystal. In other words, the crystal is vibrating, and most of the film has decoupled from it, so it's not really affecting the resonant frequency. And so this was the most natural explanation of this is that some of the helium film has become superfluid, which is well known, of course, and has simply stopped, decoupled from the crystal, doesn't move with the crystal. But the film is so thin, now it's maybe 2, 3 atomic layers thick at the most, and so it is essentially two-dimensional. And so the experimental data says that something's happening. It looks as if there's phase transition taking place. But there was a mathematical theorem due to Merman and Wagner, which said made the statement that in 2 dimensions, in a system with a continuous symmetry, which this helium, obeys the conditions of the theorem. What it said, the theorem says there's no long-range order at any finite temperature. And at the time, there was this guru of phase transitions, Lev Landau, who made the statement that the difference between the disordered phase or the high temperature phase and the ordered phase is that the ordered phase has long range order. Okay, so essentially all physicists at the time accepted that if you're talking about a phase transition, the low temperature phase had long range order. But there was a theorem due to Merman and Wagner, which said, it's a mathematical theorem, which said that in such a system, there was could no long range order. So there was this discrepancy between what looked like perfectly rigorous theory and observation. Because observation said, from this graph in this slide said, look, there is a phase transition. You can see it. It's where the experimental points break away from the expected straight line. But there's this rigorous mathematical theorem that said there's no long range order in this system in 2 dimensions. So this discrepancy between theory and experiment needed to be explained. And this is the sort of problem that David Fowler's really liked. And so he asked me to look at, to think about it, because, we discussed it for hours. And we discussed how maybe we could do something with it. And the idea is the following. Well, basically, this is just a few papers that I wrote, or we wrote, and on the subject. And as you notice that the early papers were published in the Journal of Physics, basically a British journal, which is not that, it doesn't have that high impact parameter, but that's where we published. Now, we talk just a few minutes about the physics. Okay, here's a vortex. Okay, what we have here is in the middle, we've got the fluid going round and round, just like water running down the plug hole when you pull the plug after a bath. Now, the fluid is superfluid, but superfluidity can only exist in a fluid that's not moving too fast. So we assume that most of the fluid is superfluid, and there's a vortex, it just goes round and round the center, like water running down a plug hole. Of course, because the velocity, of the fluid behaves like 1 over the distance from the center, the velocity of the fluid is very fast in the center, near the center of the vortex. And theory tells you it basically the fluid can't be superfluid there because it's trying to move too fast. So we modeled this system by saying, okay, we described a vortex by the fluid circulating round and round. And of course, the center of the vortex has to be normal fluid. And that costs you energy, or free energy, should I say. So this is just a model of the system. We regarded the helium or the two-dimensional XY magnet as a system which is like a superfluid, where you've got an order parameter with a magnitude which is basically fixed, and a phase, and the phase change as you go around a vortex. The phase changes as you go around the center by 2 pi, or some multiple of 2 pi. And so the question is, we describe the fluid, we ask the question, what can destroy superfluidity? We assume that the film is superfluid. And we wanted to know what excitations can make this fluid normal. And the only thing that can do it are these vortices. And it's very simple, because imagine we have this superfluid flowing along, say, downwards with some constant superfluid velocity, which I call U sub s. And let's suppose for some reason we've got a couple of vortices created in the superfluid. One is circulating in a clockwise direction, call that the plus vortex, it doesn't matter. And the other one's circulating in the anti-clockwise direction, call that the minus vortex. Now, one can show that this uniform superfluid flow will cause these vortices to move, one vortex to move to the left, one vortex to move to the right. And when this vortex anti-vortex pair separates off to infinity, or if you imagine this fluid flowing down the outside of a glass tube, say, these vortex and anti-vortex separate and go around to the back of the tube and then annihilate each other. What happens is the average superfluid velocity is decreased by a very small amount by this process. And of course, this process can happen over and over and over again, because we assume that this vortex anti-vortex pair, which has got finite energy and therefore will exist with finite probability, that these exist in thermal equilibrium. And so we simply say that if we've got a small average superfluid velocity relative to these, then this process will happen over and over again, and the superfluid velocity will decay to zero. And when a superfluid velocity decays to zero, that then is a normal fluid. So therefore, the superfluid is a fluid where you basically don't have any free vortices, and normal fluid is a fluid where you got a lot of isolated free vortices, so that you have dissipation. Okay, one can, you can make a bit of a theory, construct a theory of all this, and there are two parameters in the theory. One is this K, or stiffness, which is proportional to the superfluid density. And the other parameter is this Y, which we call the fugacity, or if you like, is related to the energy of the vortex core. And then there's this, you can formulate what is called a renormalization group, which tells you how, if you simply imagine increasing the vortex core size from some, it's a value A to A times E to the L, then you can say that you can work out these equations, which for how the interaction, this K, which is a proportion of the superfluid density, and this fugacity behave as a function of this parameter L. And the flows, as L increases, we start off with a system somewhere here with parameters here. So K is inversely proportional to temperature. So sorry, where's my cursor gone to? This rescaling will cause the system, increased with the scaling parameter, causes the system to become, the parameters of the system to move like this. Okay, so they either flow into a line y equals 0, or they don't. And so then we look at this diagram and we say, what does this mean? What it actually means is it splits into basically 3 regimes. One is that, okay, this C is a integration constant. You know, when you integrate these two equations of motion, you have a constant integration, of course. That's this parameter C, which can be related to the deviation from the onset temperature. And there are 3 regions. One is this parameter is where you're below TC. And in other words, this little t is negative. That just means you're slightly below the critical temperature. And that is positive. This parameter C is positive. And the flows either flow to, the y equals 0 line, which means that the fugacity has gone to 0, which means there are no vortices. Therefore, all systems which start off below this straight line correspond to a superfluid phase, because it scales to 0 fugacity, which means no vortices. However, all systems which initially lie above this straight line, they eventually flow to this fugacity increasing. And when the fugacity increases, it means that free vortices are probable, so that, and then such a system will dissipate, and therefore it's a normal system, so that if this parameter is negative, then that corresponds to a system that's non-superfluid, is normal. And region 3 is similar. So actually region 1 corresponds to a superfluid, regions 2 and 3 corresponds to normal fluid, and the critical temperature corresponds to this straight line that flows to 0 fugacity. Okay, now this all sounds very fancy. Now, the crucial predictions of our theory are the following. The first is the measured stiffness constant, which is proportional to the measured superfluid density divided by temperature, does not depend on the scaling parameter. The second thing is the superfluid density. This measures superfluid density, superfluid mass per unit area, divided by temperature, is, since this stiffness constant, this measured stiffness constant, does not depend on the scaling parameter, then if we're below TC, then this is equal to the value at L equals the value of the parameters at L equals infinity. But since if we're below TC, y of infinity is 0. So this is just k of infinity, which can be calculated. And this can be calculated to give me a number, which happens to be 2 over pi plus some constant times the square root of TC minus T. This is as long as T as you're below some critical temperature. Now, if you're just below the critical temperature, just below, then what happens is that the measured superfluid density, mass per unit area, divided by TC, is given in terms of these fundamental constants. Mass of the helium atom, Planck's constant, and the Boltzmann's constant, and this works out at about 3.5 times 10 to the minus 8 grams per square centimeter per degree Kelvin. I may have a factor of 10 wrong here. I have to check that. Now, okay, so we have an experimental prediction. Now, notice this experimental prediction is that the measured superfluid, if you're just below TC, just below, the measured superfluid density, mass per unit area, that's this rho sub S with an R on it, divided by the critical temperature, is given by this combination of fundamental constants, and which is some number. And this number is inescapable. In other words, if the theory is right, then the experiment must measure this number. If the experiments are done and they come up, and the experiment comes up with a different number to this, then our theory is wrong. And of course, fortunately, what happens is that when the experiment's done, this is a combination of quite a lot of different experimental data, some experiments by Bishop and Reppy, and some third sound experiments. So the experimental points, so they have here the superfluid density just below TC times 10 to the 9. I guess my 10 to the minus 8 should have been 10 to the 9 against the critical temperature, the transition temperature. And of course, the transition temperature is you can change that easily by simply making the helium film thicker. Because if you make the helium film thicker, you increase the onset temperature. And so we have a set of data points from different experiments, and the solid straight line is the theoretical prediction. Because remember, the theoretical prediction says that the superfluid density just below TC divided by TC is some universal constant. In other words, the slope of the straight line is theoretically predicted. So being somewhat biased myself, I would say that's a very good, the agreement between theory and experiment is pretty good. So I view this as confirmation of the theory. Now, one can do similar things. A similar theory describes the melting of a two-dimensional solid. And the two-dimensional solid can be made by simply a set of polystyrene spheres with a paramagnetic ion in it, floating on the, trapped at an air-water interface. And assuming that the melting of this solid takes place by the unbinding of dislocations, which are similar to, play a similar role to the vortices in a superfluid. So it's described by a similar type of theory. You described the solid as a set of interacting dislocations. Of course, the theory is more complicated, but the predictions are very similar. The prediction of the theory says that the Young's modulus, the measured Young's modulus, as a function of temperature, inverse temperature rather, that the system will melt when the Young's modulus takes on a particular value, which happens to be 16 pi, which is about 50. And so the theoretical prediction is this red curve here. The experiments are these points with rather large error bars. But the for the system of colloids floating on air-water interface, the agreement between theory and experiment, again, is quite good, because even the experimental points clearly follow a path, you know, like this. And so the system melts when the Young's modulus is about 50. And so this theory was based on the so-called Costas-Thouless theory, was constructed by Halpern, Nelson, and Young. And the agreement between theory and experiments were done basically by Georges Marais and co-workers. The agreement between theory and experiment in this system is, again, looks pretty good. So we can view this as a verification of the theory. Also, there's another system to which the theory applies, and that is the basically it's a cold atom system, and the theory and experiment seems to agree pretty well. There was a paper by Dalibard and company in, sorry, I've being stupid here. Oh yeah, in Nature in 2016, so that the theory agrees quite well with observation for these cold atom systems. And so the last concluding slide is some acknowledgements. I'd like to thank the now unfortunately deceased David Thouless for introducing me to this beautiful problem, David Nelson for collaboration and discussion, and of course John Reppy for many useful discussions, and of course the Nobel Committee for recognition. And I'd like to thank my wife Berit for an incredible life journey, taking us from Oxford to Torino to Birmingham to Providence. And finally, but not least, of course, my children, Karen, Jonathan, and Elizabeth, for putting up with their very strange father and his strange pursuits. So thank you very much for your attention. I'm sorry I ran over time. So that's really all I have to say.
Thank you very much. Okay, thanks for the fascinating talk. It had entertaining stories and quite good insight into the journey that you call the random walk. So I'd like to open the floor to questions. I think the best way probably would be to maybe first try and put the hands up electronically, and then I'll call upon you to ask the questions. And if this doesn't work, we can try something else. So, yeah, maybe initially people will need a bit of time
to absorb it, to
break the ice. So maybe I can start with a question. So you mentioned third sound and static versus dynamic sort of versions of the sequence.
Right, of course, yeah, with helium, of course, the experiments are of necessity dynamic, because there's no way of weighing, the superfluid, and you have to do an observation at finite frequency or finite flow velocity. So of necessity, the experiments are dynamic. So of course, one needs to to make a proper comparison between such experiments and theory, one needs an extension to dynamics, which was done by Halperin and Nelson, basically, in a series of papers. And this extension was essential for the proper interpretation of the experimental data, because you see, the experiment, if you're doing a dynamical experiment, you have a high frequency regime and a low frequency regime. And of course, to make a comparison with static theory, which has the universal predictions, you have to take the limit, basically a low frequency limit. The only trouble is, what is low frequency? Because low frequency means a frequency small relative to some characteristic frequency. And in these systems, the characteristic frequency is already extremely low. It's a matter of a few hertz. So that the real low frequency limit is really low frequency. And so to get a comparison with this static theory, where the exact predictions are, you need the dynamical theory to be able to make a proper comparison.
Okay, thank you. So are there any other questions? Questions from the audience?
Yeah.
Stefan.
Yeah, I mean, just talking about this, I mean, this reminds me a little bit of Andronikashvili's experiment, where he had this very sort of, did one repeat this in this view somehow again?
Well, it's similar. I mean, well, of course, the Andronich, remember, we're working with a thin film, which is a few atomic layers thick. So it's a bit difficult to put in a what's it called, the appropriate measuring apparatus.
Yeah.
So.
Yeah, his films were thicker. I'm pretty sure. Yeah, that's right. You have to put it very high up in the cryostat, and then it becomes a little unstable.
Right. These experiments are quite difficult to do.
Yeah. I see.
And so, but of course, with if you think about it, there are very few exact predictions in at phase transition. Because it's a two-dimensional Ising model, but as far as the other exact predictions are concerned, there really are rather few, and it's quite difficult to get a physical system which is a good representation of the theory, which has the prediction. But of course, the superfluid helium film is a perfect system, which should be a good realization of the physical system, but there's the problem of interpreting the experiments. You might think that an obvious system for which a theory should be valid would be a thin superconducting film, because again, the superconductor vortices and so on and so forth. But the trouble is that the vortex-vortex interaction in a superconductor is cut off by at a finite length scale, the penetration depth,
yeah,
which is infinite, of course, for the helium film. And so in principle, there is no transition in a two-dimensional superconductor. And so, though you can make nice two-dimensional superconducting systems, Josephson junction arrays and so on and so forth, the theory is a bit complicated because it has to take account of all the various length scales and scales involved.
Yeah. There's the lambda length as well, yeah. Yeah, that's true. Yeah, and also I think if you have a superconducting film in a solid state system, you always have to have the problem of defects where these vortices can be pinned. And helium is so extremely clean. I mean, it makes it such a nice system.
Yeah, that's also very true, right?
Yeah.
Thank you. Other questions?
I would like to give a comment, since I did the experiments on the colloidal monolayers. Meanwhile, the error bars are smaller. Hello, Mike. My name is Peter Keim.
Oh, hi, Peter. Yeah, I'm sure that the error bars have got considerably smaller.
Second order phase transition with critical fluctuations, and it's a question of time and system size. And the larger the systems are, and the longer we measure, we can make the error bars much smaller. And of course, we also measured a critical exponent. We measured this 0.369 you predicted, and David Nelson predicted for this renormalization of Young's modulus.
Right.
You got it.
Yeah, thank you, Peter. A question from Stefan Klump.
Sorry, I need to turn on my microphone, otherwise it doesn't work. Yeah, thank you very much for this nice talk. I thought you mentioned the Mermin-Wagner theorem and the discrepancy with the observation. So I was wondering, at what point when you made these predictions did it become clear how to resolve this discrepancy?
Well, I mean, the discrepancy actually occurs at a much more fundamental level, because the Mermin-Wagner theorem seems to imply that there is no phase transition in these two-dimensional systems. In other words, there's always an high temperature phase. That is if you believe in Landau's, phenomenological theory of phase transition, which says that a low temperature phase must have long range order. Now, so the discrepancy was that the rigorous mathematical theorem says that there is no long range order at any non-zero temperature in two dimensions. Now, that statement is definitive. But that statement, when you combine it with Landau's statement that the low temperature phase has long range order, then there can be those two statements imply that there can be no phase transition in these two-dimensional films, because there's no long range order on any non-zero temperature. Therefore, there can be no superfluidity. So that was the situation in the early 1970s when Thales and I started thinking about the problem, because it looked like there was no way of understanding this business, because just that the fact there could be no theory seemed to say quite definitively there is no phase transition, but experiment says look at the data, there is a phase transition. So that was the discrepancy which we managed to sort out. And so at first, when I started thinking about this, I thought, my God, this is impossible, because, you know, how can one overcome this apparently rigorous mathematical statement of the Mermin-Wagner theorem? You know, because then the first thing we had to do was to convince ourselves that the low temperature phase did not necessarily have true long-range order. Because, you know, the two-dimensional, the superfluid phase in 2 dimensions does not have long-range order, but it has finite stiffness. And similarly, a 2-dimensional crystal, you just take the harmonic theory of the low temperature phase. So you've got a finite elasticity, elastic constants, that will have no true long-range order. Then one way of picturing this is to say, okay, let's take a rubber sheet and we'll draw on this a nice triangular lattice of dots. And then we take this sheet and stretch it and compress it, you know, arbitrarily, but never tear it. So then what will happen is that the position of any dot representing a lattice point will move, you know, will have moved arbitrarily far from its starting point, so that there's no translational order in the system, because the small fluctuations are like this stretching and compressing. Okay, this causes huge displacements of the lattice points from their equilibrium positions. So there's no true long-range order in this crystal, but there's still finite elastic constants. And so we have a system which is no long-range order, but it has finite rigidity. And so, you know, in the 1970s, we had to change, you know, in 2 dimensions, you had to change your viewpoint about what is meant by an ordered phase. You know, it's a phase with finite rigidity, but no long-range order.
Okay, thank you. How did you come to that change of viewpoint? Was that more based on mathematics, or was it an idea that you had before you did the mathematics?
Well, I mean, you know, the mathematics about lack of long-range order is pretty trivial. It's just a matter of, you know, doing something like Gaussian theory with spin waves or something like that. So then the, you know, the what should we call it? You know, then the correlation function, you know, the density correlation function decays like 1 over, you know, 1 over some power, you know, distance to some negative power. And as the distance between the 2 points goes to infinity, that goes to 0, which means there's no long-range order.
Mm-hmm.
And so, mind you, you know, at the time, probably Thales and I were probably the ideal team to look at this, because Thales was a guy who understood everything. But he could recognize that you didn't actually need the long range translational order for a crystal to exist. And I was just the ignorant postdoc who'd never done any solid state physics before. And so I really had no idea that there was this major conflict. And so everything that Thales and I were doing just seemed perfectly natural. You know, it's sometimes with, you know, too much, a little bit of knowledge is a dangerous thing. And some pure ignorance is better than a little bit of knowledge. So as I say, I was the sort of guy who's, you know, was reasonably smart, but ignorant. So I wasn't affected by this this conflict. So I didn't know about that the ordered phase had to have long-range order and so on. And Thales realized, of course, that what the weakness in the arguments, the mathematical arguments were. So between us, we were okay.
Okay, thank you very much. We also had a question from a climbing enthusiast. Colin Marius Andreas Koch says, did you perform a sit start when you first climbed the Fessura Costerlitz?
Did I perform a what?
A sit start. I think it's something the young kids do these days.
Oh, good Lord, no, of course not.
Yeah.
No, I mean, look, at that time in the early 1970s, I was quite good, but the standards have gone up since then. The standards have gone up to a point where which is way beyond my abilities, even when I was at my best. So people are now doing things which would have been, would have viewed then as impossible.
Okay, thank you very much. So I don't see any remaining questions. I guess this would be a good place to wrap things up. So thank you very much for this very entertaining talk, and let's thank the speaker one more time. Okay, and we look forward to having you around in person at the earliest possibility.
I look forward to that too, but we'll have to wait and see. I have been stuck in what I call my study at home, shouting at my computer screen for the last, since January, I think, since February last year.
Yeah, so more than a year for all of us.
Right. And so I don't know about you, but I'm going crazy with this remote teaching because it's 10 times as much work as teaching in person.
Yep. Correct.
Yep.
Yep. Okay, well, so I think we can close the official part of the session. If people want to stick around and talk to each other or hang out and have chats, you're welcome to do that. I think otherwise we basically bid you farewell and look forward to the next opportunity to meet you all. So thank you very much. Bye-bye.
Welcome. I hope so. Thank you.